Welcome back to the Chidon's Academy UNN, and we are going to be continuing on stereochemistry, basically on optical activity and as how it relates to drugs. So, if you have watched the previous videos, you'll have been able to understand some of the basics concerning stereochemistry. And today, our focus is going to be on types types of chiral molecules. All right. Types of chiral molecules. So that's going to be our focus today. Now, we have talked about what chiral molecules are. We've explained exactly what chirality is all about, and one of the examples I gave was with regards to using your two hands. And I said that when you have a compound that the mirror image is not superimposable on that compound, then that compound is chiral. We tried to explain some of the elements that are necessary to define chirality. We talked about the different points of inversion, we talk about plane of symmetry, and so on and so forth. So you can always refer to the previous video so you can get appropriate understanding. So when we talk about chiral molecules, basically, broadly, we have two classes or two types of chiral molecules. We have point chirality, that is when we talk about chirality with regards to stereocenter or stereogenic center. Then we also have a chirality that has nothing to do with stereocenter or stereogenic center, and that kind of chirality, we call that either axial or planar. So let me put that now. So chirality with stereocenter, with stereocenter or stereogenic center, we refer to that as point chirality. Then the second one is without. So I will just stop at without, and what I mean by without is without stereocenter or stereogenic center. Without, we refer to that, we have two types of that. We have the axial, and we have the planar. We have the axial and the planar chirality. So these are the two types of chiral molecules we have. Chiral molecules that their chirality is with regards to a stereocenter or a stereogenic center. Then we have chiral molecules that have their chirality without a stereocenter or stereogenic center. So the next question you may want to ask is, what is a stereocenter, or what is a stereogenic center? So when we refer to a stereocenter, we're simply talking about a point or a point in a molecule or a compound wherein if you change two substituent groups in that particular compound, you're going to obtain another compound whose image is not superimposable on the mirror image. What I simply refer to that, when I talk about that, I'll just have to use an example to explain to you. And one common example we usually use is carbon. Now let us look at carbon, and let us look at a compound like this. Now remember, we have our wedge bond and our hash bond. So let's use our wedge bond and our hash bond. Yeah. And then we have our stick bond here. So let's assume that what we have here is, let's say, H. What we have here is CH3. What we have here, let's say what we have here is OH, and what we have here, we have COOH. Now, when you have a carbon compound that has four different substituents, that carbon is referred to as a stereocenter, because these substituents are different, and when you begin to interchange them, you can be able to get a mirror image of this particular compound that is not superimposable on each other. So that's exactly what we're talking about when we talk about stereocenter or stereogenic center. So it simply means that the chirality is in reference to that particular point or that particular center. That is why it's also referred to as point chirality. Are we together now? So, but then when we're talking about chirality without stereocenter or stereogenic center. It simply means that there's no point specifically that you can look at and say, okay, from here you can now begin to talk about the chirality of the molecule. So, but then when we get to this particular point, I will explain the axial chirality and I will explain the planar chirality. So before we go on, let me talk about the structure of tetrahedral molecule, the representation of tetrahedral tetrahedral molecules. Now when we talk about tetrahedral molecule, we're talking about molecules that have four bonds, four different bonds, and usually what we have is carbon. So tetrahedral molecules, the way we represent them, I've been using it all the while. So I'll still come back to my example. The way we usually represent it is that it usually has four bonds. Two of the bonds is usually referred to as stick bond or solid bond. So these bonds here, these two bonds here, we can either call them stick, or solid solid bonds. We can call them stick or solid bond. We can call them stick or solid bond. Sorry for this. Let me just rewrite this so you can see it very clearly. Solid stick or solid bond. So that's the name we call this kind of bonds. Then we have these two bonds. Now remember when I was talking about why we exactly have to use this is because when you have these bonds, one of the bonds is coming out of the plane and the other one is going behind the plane. So the bond that is usually used to represent the bond that is coming out of the plane is this particular bond, and so far so good, you must have known what the name is. This is referred to as the wedge bond. Another name for wedge bond is beta bond. Now it represents the bond that is coming out of the plane. Then this particular bond we have here, we refer to it as hash bond. Some other persons could also refer to it as dashed bonds. So, but dash, hash, whatever, you already know what it simply refers to. So you can refer to it as dash bond or hash bond. And that name again, you can call it alpha bond. So the hash bond is also referred to as alpha bond, while the wedge bond is also referred to as beta bond. Meanwhile, the other bond that is not hash or wedge is referred to as stick or solid bond. Now, stick or solid bond. Now, this kind of formula, what we usually refer to it as, we call it skeletal formula. So of skeletal structure. We can call it skeletal formula, or we call it skeletal structure. So of the compound. Now you can actually be able to use the skeletal structure for open chain compound like this. We could also want to use it for a cyclic compound. For example, you can have a compound like this. Let's just draw a compound. You can have a compound like this. Yeah, and I'm gonna be showing you something right here. So I understand what I'm saying. Yeah. Then let's look at this. And then let's look at this. Yeah. So here we have a cyclic compound, and here we're also having our wedge bond, hash bond, stick bond. So we're still having a skeletal structure being used to represent this. Now I said the wedge bond is representing what's coming out from the plane, and the hash bond is representing what is going behind the plane. Now with this particular structure, you can be able to tell exactly what elements are supposed to be around this particular structure. Now it is very imperative that you understand that sometimes when chemical structures are drawn, they will not tell you exactly what is there, but as a science student, you're supposed to know exactly what is there. Now, when you find structure like this is already like a hexacyclic ring. So what we have here is carbon, and automatically it has two hydrogen attached to it. So you can always be able to expand the structure to see what actually contains. Then when you have any bond that ends without anything at the end, it simply means that what you have there is a methyl group. And when I say methyl group, I'm actually referring to CH3. So it simply means that what we have here is CH3, CH3. Now at this particular point, we have another carbon here. So but the carbon also is connected to a CH3 bond, because at this particular end there's nothing there. So what it simply means that there's a methyl group that is attached at this particular end. So this is a methyl group CH3. This is a carbon connected here. When you have one, two connections, it means that you have just two connections free, and what we have there is actually what hydrogen, because there's nothing there. Now another thing again you have to take note of is, for example, if you look at this carbon, we know that this carbon is connected to this and this methyl group. The next question you want to ask yourself is, so where is the last bond going to? Now anytime you find a wedge bond, the next associated bond to it will always be a hash bond. If you find a hash bond, the next associated bond to it will always be a wedge bond. So the implication is that in this particular point, if you want to draw the full structure, you need to also understand that you have a hash bond that has hydrogen at this point. And in this particular one, it simply means you have a wedge bond that have hydrogen at this point. So you can now say we have our complete four bonds, our complete four bonds. I don't know if you're getting it now. So that's exactly what you have to work on. Then another important instruction you have to pay when you're working, or pay a close attention to when you're working with wedge and hash bond, is that when you are drawing your wedge and hash bond, you don't draw it opposites. You draw them adjacently. So you can always find out that they come together. They come together. You don't draw wedge and hash bond in this format. Now let me just give an illustration. For example, you have a hash bond here. Let's assume you now have one stick bond, then you now have a wedge bond, and then okay, let's draw this straight. A stick bond. Now this is not accepted. You can't have a wedge bond directly opposite a hash bond. This is not accepted. So what you can be able to do is to have the wedge bond and the hash bond adjacently. You can put this one at the top, put this one down, anyhow you arrange it, but they must always appear adjacent to each other. So that's a skeletal structure, skeletal formula. And like I said, you can use it for open chain molecules and you can use it for cyclic molecules. So meanwhile, we have other form of projections that you can able to use to represent these structures. We have the seahorse projection, we have the Howard's projection, and then we also have the cyclic projection and conformers. So let me just write them out. We have the sawhorse projection, we have the sawhorse projection, we have the Howard's projection, we also have the cyclic projections and other conformations. So we also have the cyclic projection and other conformations. So some of them are used for open chains, some of them are used to represent closed chains. So but overall, for the purpose of this particular discourse, we are focusing on the skeletal formula or the skeletal structure. So the next thing we're going to be moving at now is for us to be able to see how to identify chiral centers now in different elements. Now usually when we talk about chirality, usually what comes to people's mind is an asymmetric carbon, a chiral carbon. I don't know if you're getting it now. Now usually when you are representing chiral carbon, that's a carbon that contains four different substituents. It's usually recommended that you put an aesthetic, usually represented by an aesthetic. If you find a chiral center, usually you have an aesthetic attached to that particular carbon that has four different substituents. So but then apart from carbon, there are other elements that can exhibit chirality, and such elements, we have silicon, that is Si, we have phosphorus, we have nitrogen, we also have sulfur. So we can have a sulfur chiral center, we can have a nitrogen chiral center, we can have a phosphorus chiral center, we can have a silicon chiral center. So but then what basically you need to understand is to know how to identify chiral centers. So the moment you can work it out with carbon, you can be able to make progress with these other ones, because they are not difficult, especially when you have understood the carbon aspect. The idea behind it is we have four different substituents on that particular carbon, and with that you can also relate with it. So let's go into carbon and see the way to identify different chiral centers in carbon. We'll look at open chain. We'll also look at cyclic compounds. So let's make progress. So we'll be looking at some open chains, like I mentioned. We'll start with carbon, open chain. Now let me draw a structure for you. For example, let's assume we have something like this. Let's assume we have something like this. And then we are being asked, sorry, no, it's directly connected to the carbon. So let me just write it this way. History. So you are being asked if this carbon is a chiral center, that's a stereo center, a stereogenic center. Now what you just simply need to do is to check the four substituents that are connected to this particular carbon. So since we have hydrogen and hydrogen, automatically this carbon is not a chiral center because the substituents, we have two substituents that are similar. Automatically it cancels out chirality. Remember what we talked about in the first point. It means we can go to have an axis of symmetry that cuts through this, and this. So the moment you have an axis of symmetry that can cut through this, you have hydrogen on this side, hydrogen on this side. It means that the mirror images are superimposable. You can always refer to the previous video for you to understand what I'm talking about right now. I've explained it appropriately. So the only way you can have a chiral carbon is if and only if, basically that's the basic, is if you have four different substituents. So but then there are other factors that go beyond this. But first of all, you must have established that the carbon has four different substituents before you begin to look at other factors that can contribute to its chirality. So let me just look at another particular structure and let us see how it goes. So let's look at this particular structure where you have this guy and you have this guy, and then you have this guy. So if you look at this particular structure, what we have here is a methyl group, what we have here is an ethyl group, and what we have here is hydroxyl group, and what we have here is our hydrogen. These are four different compounds. Automatically this is a chiral center, and automatically this is a chiral compound because the mirror image of this is not superimposable on this particular structure. And like I told you, when you have a chiral center, usually how we indicate it is by using of asterisk. So are you seeing how exactly you can go to identify stereocenters or chiral center? Now when you have identified stereocenter or chiral center, then you can now be able to check if the molecule is actually going to be chiral at the end of the day, because in one particular compound you can have several chiral centers, and we're going to be looking at an example for me to buttress this particular point. So let us look at this particular example we have here. So we're already continuing now with the cyclic compounds. We've talked about open chain carbon structures, and then how to identify if there are chiral centers there, and also to know if the structure totally is chiral. So we're going to be looking at this cyclic compounds. First of all, we are going to be identifying where we have stereo centers, which we also refer to as stereogenic centers, or we call it chiral center. And then when we identify if there's a chiral center, they will now know if the molecule overall is chiral. So let us look at the first one. So the first one here we have is a benzene ring. Now, automatically, the moment you're having double bonds, it simply means that what we have here is sp2 hybridized carbon. The implication is that the carbon is not having four different substituents. This carbon is already double bonded to the carbon, double bonded to this carbon, and these bonds, they rotate. They are not stable, they are not in fixed positions, they rotate. So the implication is that the carbon do not have any none of the carbons here have four different substituents on them. So this carbon has carbon, carbon, hydrogen, and then carbon. So this particular carbon has carbon, 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 one hydrogen. This carbon has carbon, 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 one hydrogen. So the implication is that all the carbons here, none of them are chiral because they don't have four different substituents. So the implication is that this compound overall is a chiral. It means it's not a chiral compound. So let us look at this other compound here. What we have is 6 carbon. So this is cyclohexane. This is cyclohexane. Now this cyclohexane, you find out that this carbon, we have carbon here, but then now let us look at the full structure because this is a cyclic compound. This carbon now we have carbon, 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 carbon. Okay, for you to understand better, so that you can understand what I'm saying, let me just write out for each of these carbon, let us write out what they are going to have like on both sides. So let us use this particular carbon here. So this carbon is going to have the first carbon here, this will be CH2, second carbon here, this will be CH2, third carbon here, this will be CH2, fourth carbon, this will be CH2, and then the fifth carbon, this will be CH2. So this particular carbon going from this side, you have 1, 2, 3, 4, 5. That is 1, 2, 3, 4, 5 carbon. If you go from this side, you have 1, 2, 3, 4, 5. You still have the same combination. The implication is that it's already having two same constituents. And when you now consider the fact that there's hydrogen and hydrogen here, it means that this carbon is not chiral, and this carbon is same as this other carbon because there's no other attachment to any of them. The implication is that there's no chiral center here, and since there's no chiral center, the compound itself overall is also achiral, because we can also see points of inversion, and we can also have axis of symmetry, because anywhere you divide it, you have mirror images that are superimposable on each other. So let us look at this particular compound, and this is compound number 3. Now this compound has a methyl substituent. This compound has a methyl substituent, but the question is the carbon chiral? We already know that from here, looking at this particular structure, this particular carbon, if you look at this particular carbon and start counting CH2, 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 then CH, CH3, and then you look from this particular point, this is CH3, and go back that way, the two combinations, let me just write them out so you can understand. Let us use this carbon before we talk about this guy. Let us use this carbon. For this particular carbon, we have, going through this way, we have CH2, we have CH2, then here we also have CH2, then here we have CH2, then here we have our CH3. So, but then if you are going through this way, you have the CH3, then you now have your CH2, you now have your CH2, then you have your CH2, and then you have your CH2. So why the CH3 and this one is at the other end, this one is at the other end. Now these two substituents from this point and this point, they are different. But then there are two hydrogens. Automatically, this carbon cannot be a stereocenter because we have hydrogen and hydrogen. So let us look at this particular carbon. This particular carbon is just like this carbon here, because if you run from this point this way, you will get this particular compound. If you run from this point this way, you have this particular compound. And then if you put a plane of symmetry across this, you will have mirror images that are superimposable on each other. It is not a chiral center, and there's also a plane of symmetry. So automatically, this compound also is also an achiral compound. It's also an achiral compound. So let us look at this particular compound now. Now this particular compound is quite tricky. You may look at it and be like, oh, we now have different substituents. How about that? Now if you look at this particular compound, let's look at this particular carbon. At least we already know that this is one substituent, this one substituent, this one substituent, and then we have hydrogen. Let us look at this particular compound and then run down what the components are going to be looking like. So let us start from this side. So what we have here is CH2, second one, CH2, then we have CHOH, then we have CH2, and then we have CH2. Then let us run from this opposite side. Let's see what we have. CH2, that's CH2. We have CH2, CH2. We have CHOH. We have CHOH. We have CH2, CH2. We have CH2, CH2. It simply means that if you go through this way and you go through this way, you have the same compound. The moment you're already having two same substituents on one carbon, that carbon automatically is no longer a chiral center. So it means that this carbon here is not a chiral center. In similar vein, if you consider this, where you now have OH, what we now be having here will be CH3. And if you go through this way or that way, you will have the same thing at that particular point. So it means that these two substituents automatically have also made this place not to be a chiral center. And the implication is that you don't have any chiral center in this particular carbon. These ones are already as, because you have two hydrogen, two hydrogen, two hydrogen, two hydrogen, so they're already cancelled out of the game. Now, you don't have chiral center. The next question you want to ask yourself is, all right, the molecule overall, is it chiral? It is not chiral. You can already see for yourself. The moment you have a plane of symmetry that divides this, here is superimposable on this. They are same images, they are mirror images of each other. So automatically, compound number 4 is also a chiral. Compound number 4 is also a chiral. Compound number 4 is also a chiral. So let us look at the compound number 5. I'll be cleaning this so that you can wait to see the compound number 5, because compound number 5 is actually very interesting. So I understand what we're talking about here. So let's look at compound number 5. Now let us look at this carbon, because this carbon already has something that looks like 3 substituents, but let us see if it's right. So we'll start from here and then we'll go from here. So let's start with this. What we have here is CH2. What we have here is CH2. What we have here is CH. What we have here is CH. What we have here is CH2. So let us come from this point. Here we have here is CH2, CH, CH, CH2, CH2. Now, if you look at this particular compound, you find out that the progression from here and the progression here, they are not the same thing. They are not the same thing. So we have our double bonded after the first two carbons from this particular point, and then we have our double bond here after the very first carbon from this particular point. So it means that the substituent here is different from the substituent here, and you already have a methyl group and you have hydrogen. The implication is that here automatically is a chiral center. So we have found a compound that has a chiral center. And the next question is the compound overall chiral? Yes, because if you put a plane of symmetry here, there's a double bond here, but there's no double bond here. So automatically these two places are not mirror images of each other. Automatically this compound is a chiral compound. So we have been able to get one chiral compound. So let us progress to compound number 6. From what I have done so far with number 3, you can already see for yourself that compound number 6 automatically is a chiral, because this substituent here, if you walk down this way and walk down this way, they are two same substituents. The moment you have two substituents that are the same, automatically that compound is a chiral. And another thing again is that you can already see a plane or symmetry. So if you have a line that crosses across this place, here is equivalent to this particular point. So automatically this compound is regarded as a chiral compound. It cannot rotate the plane of plane polarized light. So let us look at this particular compound now. Looking at what we have here too, if you are working with this compound, let us write out what it's going to look like for this particular compound. We are going to be having CH2 here, CH2, then we have oxygen, then we have CH2, and we have CH2. Now let us run it down from this side. Here will also be CH2, here will also be CH2, here will be oxygen, CH2, CH2. So you can already see for yourself that if you go this way or you go this way, you have same compound. Automatically these substituents and these substituents are the same. The implication is that this carbon center is not a chiral center. Another thing again you want to ask yourself is, okay, what about the overall compound? Is it chiral? Now let us check. If you have a plane of symmetry that cuts through the bromine, carbon, and oxygen, this side automatically will be equivalent to this side. So it simply means that there's a plane of symmetry. Automatically, compound number 7 is going to be a chiral compound. So let us look at our last compound under cyclic compounds when we talk about chirality. Now let us consider this particular case. Let us run what is here and let's run what is here so that we can see the difference between this and this. So for this guy we have CH2, here we have CH2, here we have CH2, and then we have our oxygen and the final CH2. Now if we run it from this particular direction, that's the clockwise direction, we will now have our CH2 first, then we have our oxygen, then we have our CH2, we have our CH2, and then we have our CH2. Now take note of the two compounds. You have oxygen at the beginning here, and then you have oxygen at the end here. These two compounds are not exactly the same. So the implication is that the substituents from this end and the substituent from this end are not the same. And this substituent bromine is not even the same. And then we have hydrogen. The implication is that we have 4 different substituents on this particular carbon. And by implication, that carbon is a chiral center because it has four different substituents. Then the next question you want to ask yourself, as always, is what about the overall compound? Is it chiral? Yes, the compound is chiral. How do I know that? Can you see that there's no plane of symmetry that can divide it? Because the moment you have a line going through this way, you have oxygen here, but there's no oxygen here. Automatically, these two sides are not the same. Even if you say you want to divide it this way, there's a bromine here, there's no bromine here. So automatically, these two sides are not the same. There's no place you can find a plane of symmetry, and you already have a chiral center. So overall, compound number 8 is a chiral compound. So the implication is that you should be able to identify stereocenters, stereogenic centers, or chiral centers in carbon-based compounds, whether in open chain or in cyclic compounds, at any point in time. Now, I told you before that there are other elements that exhibit chirality. We have silicon, we have nitrogen, we have phosphorus, we have sulfur, and like I said before, the way we have for four different substituents on carbon, that's the same way for each of these elements: phosphorus, nitrogen, sulfur, silicon. The moment you have four different substituents on them, automatically you're already talking about you're already talking about having a chiral center there, a stereo center, or your stereogenic center. So when you go through your materials and then you find things related to silicon, sulfur, phosphorus, nitrogen, just know that what we're still working with is something related to carbon. Four different substituents and you are good to go. Thank you.